It's time to start the second part of the course. We'll do that with the first lecture on tectonics and earthquakes, but all of this is really part of the section of the course that I call the geomorphology section of the course. Geomorphology refers to the landforms that we see on the surface of the earth and the processes that cause them to be formed. And tectonics and earthquakes is the first stop in understanding those. After we do that, we'll have another lecture and look into landforms of deformation that take place on the crust as a result of tectonics, including volcanic activity. And then we'll move on to weathering, mass wasting, and karst. Next module, we'll launch right into a full exploration of geomorphology by looking at rivers, coastal systems, and glacial landscapes as well. But let's start off with some very basic geology. This is not a geology class, of course, it's a geography class, but there's some important geology that is behind tectonics in helping us to understand the physical geography of the surface of the Earth. And part of that is just the basic structure of the planet. The planet has several layers in it, beginning with a core in the very middle of it. That core is metallic in nature. There's both an inner core, which is solid, and an outer core, which is more molten. And the fact that they are spinning, it creates geomagnetism, or the magnetic field of the planet, which is super important, not only because it helps a north arrow point the right way on a compass, but because it provides a lot of protection from the sun's dangerous energy. Above that is a more rock-like layer of the planet, which is the most massive, and that's the mantle. At the very surface of the mantle, there begins to be a transition from a more molten and plastic-like material into what we would think of more as solid rock. And that takes place on a thin layer called the asthenosphere, upon which the solid crust rests and essentially floats and moves around. That's the lithosphere, the solid Earth, and it consists essentially of oceanic material and continental material, which will become important here in just a second. All of the crustal material is moving around, and the planet itself is broken into what are referred to as plates. These are essentially sections of crust that are moving and pushing against one another at different rates as a result of energy that is flowing from the center of the Earth. Each of these plates consists potentially of both oceanic material and continental material, but some of them are dominated by one or the other. And it's important to note that the oceanic plate material is much denser and much thinner than the oceanic material, which is more buoyant essentially on the asthenosphere. As the plates move, they interact with one another, and those interactions produce all sorts of interesting phenomena. The classic area of plate interaction is where two plates are pulling apart from one another or spreading. These are also referred to as constructive plate boundaries because new plate gets made where the two plates pull apart from one another. This typically happens in oceanic areas, and there are a large number of oceanic spreading centers, but there are a few areas in continental zones that also have rift areas associated with them. If plates are pulling apart in one part of the planet, that means they're coming together in another part of the planet. And the convergent boundaries and subduction zones are the major places where plates that are being created on one side are destroyed on the other side. So these are the destructive plate boundaries. Typically they occur where one oceanic plate, which is denser than a continental one, essentially dives underneath the continental plate. But there are a number of places, particularly in the Pacific, where two oceanic zones collide with one another and the denser one plunges into the mantle. One of the things that's really important about both of these boundaries is that they're associated with a lot of volcanic activity. In the case of divergence, where the plates pull apart, essentially the mantle comes out of those areas, and there are large numbers of volcanoes and volcanic activity that are associated with that divergence. In subduction, where one plate is being destroyed by the other plate, it causes great heating on usually the plate that is above the continental plate, and that in turn leads to volcanic activity as well. In both of these places, though, you also have, in addition to volcanic activity, a lot of what is called deformation, where the crust is being broken apart or bent or folded, things that we'll talk about later. This is a diagram right here that shows the idea of a spreading center between South America and Africa, a constructive plate margin. And then on the other side of South America, we have subduction occurring where the oceanic plate of the Pacific Ocean is diving underneath of South America, causing volcanoes both in the Andes range, but also in the oceanic rift zone as well. Other plate boundaries that are very important include collision areas, and these are sometimes referred to as conservative plate boundaries. Two continental zones generally coming together and pushing against one another. Nothing is being created or destroyed, but there's a huge amount of tectonic activity that takes place in these zones, and as a result there's a huge amount of deformation that occurs. Translation is another conservative plate boundary. And these are areas where two plates, generally continental plates, but not always, are next to each other and moving with respect to one another, but they're not essentially colliding into one another. So instead, there's a lateral movement between the two zones. And again, that lateral movement creates a lot of deformation. It leads to the formation of mountains, to the folding, to the warping, to the faulting, and the other things that I've already mentioned. We'll get back to this idea of deformation of the crust later. Now there's one other type of, not really movement, but it's an important type of tectonic activity that's worth talking about, which is sort of an exception to plate tectonics, and those are hotspots. Hotspots are essentially places on the surface of the Earth where when a plate riding over the top of it, magma coming up from underneath in the mantle area burns a hole through the crust itself, leading to a chain of volcanoes as a result of the plate moving over that hot spot. The classic example is the Hawaiian Islands, which are a chain of islands created essentially by the Pacific plate moving over the hot spot. But there are lots of other examples of this as well. One thing that's notable about hotspots is the volcanoes that are found there are very similar in many respects to what you find in a spreading center, because you have more of this pure mantle-like material coming up to the surface of the Earth. This is a map that we'll get back to that shows volcanoes and shows plate boundaries and the types of plate boundaries, and I recommend that you take a look at it in the textbook. One of the big products of tectonic activity is, of course, earthquakes. What causes an earthquake is when plates are moving against one another, either next to each other, sideways, or they're colliding into one another, and they're pulling apart. And the tectonic plates themselves exert a huge amount of tectonic pressure on the surface of the Earth. Friction points that are found within the plate or on the edges of the plate essentially keeps the plate from moving. But eventually there's so much tectonic energy causing the plate to move that zones of rupture will take place where the friction is overcome. That releases energy and causes the plates to move and leads to an earthquake as well. The size of the rupture zone and the amount of the energy released has a direct impact on how large the earthquake is. Sometimes these rupture zones are relatively small, sometimes they're very large, and sometimes they last a huge amount of time and release a lot of energy, and those are, of course, the larger earthquakes. Now, these ruptures often take place at major crustal boundaries. But plates have many fractures in them, or fault lines, and the ruptures take place in those areas as well. They take place essentially on areas that can be identified as epicenters, which is the place of origin of the rupture that occurs on the surface of the Earth. Here's a map that shows the San Andreas Fault, which is the boundary line between the Pacific Plate to the west and the North American Plate to the east. The San Andreas Fault is a major plate boundary, but you can see that there are large numbers of other fractures found all along the San Andreas Fault because the deformation of the crust is so great in this area. And many of these faults are often responsible for large earthquakes in the area. Tectonic theory helps us to understand why earthquakes occur, and also gives us at least some sense of an ability to predict when earthquakes will take place, because the theory essentially helps us to model how earthquakes are taking place and what the risk of a particular part of the world is with having earthquakes. It's based, of course, on observations of earthquakes, the patterns that are found, large and small, and studying what has happened in the past as well, or the paleoseismology of an area. Many parts of the world that are on very active zones have areas that have not experienced an earthquake in quite some time. That's referred to as a seismic gap, and it's often a good indication that a strong earthquake will occur there in the coming future. And increasingly, seismologists, the scientists who study earthquakes, are able to measure tectonic strain, and hopefully in the future they will be able to predict when earthquakes are likely to take place by identifying these areas of strain and the patterns we found in the past and classifying how these patterns take place. One of the things you'll be doing in Physical Geography Assignment number 5 is using the theory of plate tectonics to help understand how seismologists assess risk and hazard and predict an earthquake in an area. But the use of the term predict is a little problematic because the science is still quite incomplete, and we don't really predict an earthquake like we predict weather. Instead, what we do is we predict that there's a likelihood that a large earthquake will take place in an area over the next 10, 15, or 20 years. Earthquakes are still mostly unpredictable, and the size of them is often not completely understood. Small quakes often come before a large earthquake occurs, and they certainly come after one. But those small quakes release only a very small amount of the energy that's packed into a really large-scale tectonic event. And those large earthquakes are still inevitable and still will take place, and for the most part are unpredicted as well. These are things you can explore in a little bit more depth by taking a look at the text and also in the physical geography assignment.